So we're looking at our notes today for 9.7, which, believe it or not, is the end of our section, because we did that a little bit out of order with 9.8 coming first. And as you're going through this video, I'm just going to say that if you get to a question where you're having trouble, we're going to go over this in class again, so don't worry too much about that. But you can remember to pause, rewind it, look over stuff again, try questions before you get to them. Basically the same things that you'd be doing in class, try and do as you're doing this video. But looking through that first question, and again, basically this is always going to be written there. So I would suggest maybe trying filling that in before we get to that. But if I was trying to fill in this pattern, and this is kind of introducing the concept that we're covering, if I tried and guess how many triangles are going to be in stage 9, those small triangles, I can see that if I make a pattern with those stages, stage 1, stage 2, stage 3, if I count how many triangles I start with, I have 1 triangle in the first stage, 4 triangles in the second stage, 3 triangles if I counted all these up in stage 3. So what I used as my pattern here was, we know it's going to be 81 triangles for stage 9, because based on what I see in my other pattern, I always take that stage and square it for my my total. I have 1, then 4, then 9. That's just doing 1 squared, 2 squared, and 3 squared, so that means 9. For stage 9 must mean 81, so that's 9 squared. But looking into those 3 topics, linear, quadratic, exponential models, we've pretty much seen all of these at one point or another, and that's where we're filling in for that first part. Linear, quadratic, exponential functions, we've all studied those. Those are going to be used to model different sets. And going into those 3 different functions there, we have our equations for each. So let me get into that function. We had y equals mx plus b. That's our first linear equation that we saw. Quadratic, that's the section we just pretty much worked through with the y equals ax squared plus bx plus c. Remember the shapes that those make, that's going to be a parabola. And exponential, we had these in terms of a lot of word problems in this section, interest, things like that. About was your exponential, basically growth function right here. And when we get down to these questions, so you have those questions in front of you, I would suggest trying to do those practice questions first. We're going to look at those solutions basically, but try and see how many of them you can do by yourself, and then use these notes to go back and check. But if I was to graph each set of points, starting over here on the left, again, graphing in the points just means filling them on the chart. If I have -1, -2, graph that point, 0, -1, 1, 0, 3, 2. Make sure if we graph these points, we can fill those in with basically a smooth line, so that line goes through all those points. That would be your linear equation. If I can just make all those points in a straight line, makes sense that that would be linear. If I try it with the next one, 0, 0 is at the origin, 1, 1, -1, and -0.5 is about right there. And 2 and 3, I can see that if I was trying to form our line here, so I had that dotted line along there with it, that would form your exponential graph. Again, not the entire exponential, this would keep going in both directions, but we can see that that's going to be a little bit more of a slope, so not just a straight line like what we saw before. And next one goes a little bit off the page, -2, 11, and what I use is a scale of 2, so -2, 11, -1 and 5, 1 and 5, remember because you have that symmetry, and 0 and 3 would form your quadratic, because I would have tail going down. It doesn't go all the way back up according to our points, but we can kind of imagine if I filled that in with our line, that would form your quadratic function. So moving on, if I have the x values in a set of data pairs, if I see that they have a common difference, which is what you always want to check for first, and what I have pretty much on the left side of these charts here are common differences. Common difference of 1 if you're just counting from one over to the other. We can analyze that to find the best model, and that's either going to be, again, linear, quadratic, or exponential to start with. So a linear function is if the y values have a common difference, and that part's important too. So not only do we have a common difference for the x values, but we can see in this first example, y values are always increasing by 3, so that is also a common difference for the y values. That's linear. Exponential is if I don't have a common difference, I'm not adding the same thing every time in the second table. Instead, I'm multiplying that same amount. So we use that if you have a common ratio, not a common difference. That would be exponential. And again, we can kind of see here, y values have a common difference of 3 in your first table. That's linear. Y values have a common ratio of 2. That would be exponential. But when I don't have either, if I have a quadratic function, that's if I have second differences that are constant, not the first differences like what we saw with our linear. So if I have this table here, again, first we want to check to make sure that your x's all have a common difference. Otherwise, can't really compare the y's directly. But what I see here is that when I try and add all the y's, or not add all the y's, just go from one to the other. From 1 to -1, that's subtracting 2. From -1 to 1, that's adding 4, that's adding 2. From 1 to 7 is adding 6, and from 7 to 17 is adding 10. So if I try to see the first differences, there's not really a sort of pattern there. But if I then find the second differences, so looking at these numbers, from -2 to 2, that's adding 4. 2 to 6, that's adding 4. 6 to 10, adding 4. So you can see that our second differences have that common difference of 4. So that is going to be constant. So we know that works with a quadratic. Again, not the first differences, that would be linear. Second differences, if those are constant, that's going to be quadratic. So again, try these next couple practice questions before we get to them. But if I have these next data pairs, let's see if we can figure out which function models those best. And again, pause if you need to try these ahead of time. But looking at those charts, you don't really have to graph these, but if I want to see what function models these best, I'm going to start with my XY chart. For that first one, -3, 9, -2, 5, -1, 1, 0, -3, 1, -7. If I see that the X differences are all constant, the Y differences are all constant as well, that's a common difference of -4, then I see that this is linear. Again, we don't need to worry about second differences. The first differences are all the same. For our next table, if I put those again into a table with my ordered pairs, see that the x's first of all have a common difference. Want to make sure that that works first. When I go to my first differences, it doesn't look like I have a consistent number here. I'm not increasing by the same amount every time. But just like on that last example, when I go to my second differences, I see that that second difference is always -0.5. So if I'm going -0.5 every second difference, remember second difference is always being the same, that -0.5, that's going to be best used with a quadratic. And our last example, if I use that table again, x values are all common difference, so that's +1, looks good. For your y values, we don't really have a common difference either the first time or the second time. Adding 0.5, adding 1, adding 2, adding 4. Doesn't quite work with either first or second, but if I notice that they're all being multiplied by 2, remember that was a common ratio, so that means that's going to be an exponential model. And again, you could see examples of either of those. And let's look back to our last example here, trying to put those in terms of our real world problems. And that's just kind of pointing out that if you have measurements in real life, they're not really going to follow an exact pattern. The best thing we can do is model those, not really come up with an exact solution. But say, for example, you have a used car. You buy it for $12,575. Again, that's if you start with like year 0. You just bought the car. Over a certain amount of years, we can see the value of that car is going down. And again, in terms of how much it's going down, you could find out the common differences. But what I did instead is I used the common ratio. Got a little bit lazier. I didn't really list each fraction, but the way that we can do a ratio, I just take my number divided by the number that came before it. So my first example, I take 1165, divide that by the one that comes before, 12,575. That gets us about 0.88. If I try that again, if I have this 9750, divide that by the 11,000 that came before it, that should come out to around 0.88 again. Divide these again, so ratio of 85, about 8,500 to 9,750. We get that ratio slightly different, so you see it's not exactly the same pattern, but they're close enough that if it's, again, 7540 over 8520, that's always pretty much your same ratio. And remember, whenever we're using a same ratio, that's going to mean it's an exponential model. And we've also included there, it asks us to, well, it doesn't really ask us to graph it, but you can put a graph there basically to just help you like picture what that's going to look like. Again, just by your graph, you can tell that it's not an exact straight line, and it's not really quadratic either. So from there, you can tell it's exponential. But again, the table also backed up your answer that that's exponential. And if I'm trying to put that in an equation, it's been a while, but remember for the exponential equation, we have our starting amount first. So we started with that car being 12,575. Then we had our growth rate, which in this case is depreciating, so that's less than 1. 0.88, and that's raised to the x power for however many years you want to own that car. So trying that next example, again, see if we can do those first before we get to it. But looking at that question, now we're talking about theater company income, which again won't be exact because we're talking about real life incomes. But if I start in that first year of the theater, well, I guess call it year 0, if you start out with the income of $18,254, if I'm going to that first year, so the next year's income, that's an increase of $476, which, again, you could try ratios on this too, but the first thing I did was look at those increases in terms of like the actual total from one to the other is adding 476. Then if I want to go to the year after that, I'm adding 485 to that income. Year after that is adding 480. Year after that is adding 480. So even though these aren't quite exactly the same, they're not all the same exact common difference. We can see that they're close enough for our real life example that this is considered linear. We're not always having that straight 480, but if I'm trying to make an equation, remember that 480 is going to be basically your slope, so that's how much you're increasing, going up 480 every time you increase 1 year. So that's like a rise over run of 480. And then again, just like with our last one, we have our starting amount, which is like your y-intercept. So that's 18,254. If you want to make that an equation, we're using both the slope and we're using the starting amount as your linear model. Again, not exact, but close enough that we can model that linear. So make sure to look this over, pause, rewind again, see if you want to see those solved again. We'll get these covered in class.